Okay, so hello everyone. Welcome to the talk, what C++ developers should know about globals, and in parentheses, the linker. Alternate title for this talk, things I never wanted to know about globals and linkers, but was forced to find out anyway. That's probably a more accurate summary of how I came by this knowledge. I'm not a build engineer. I'm not a linker dev. I actually work in high frequency trading. So I came by this knowledge kind of incidentally, but I think that's okay. Most C++ developers, in my experience, are not experts on the linker. So maybe this will make the talk a bit more relatable. Okay, so globals. I've never seen code that, a code base and thought to myself, wow, there's not enough globals here. If there were only more globals, this code would be so much better. Please. So the talk's not an endorsement of, yes, sprinkle globals everywhere once you know how to use them. But in my experience, there are things that are best done using globals. So here's 3 examples that I've used firsthand often. So logging, intrusive performance profiling, and polymorphic factories. So logging is kind of a canonical example. So let me just pick on intrusive performance profiling. Typically you'll have macros in your code that record, cycle counters or other information. They can be enabled and disabled by macros. They have to record that information somewhere, and you don't really want to pass down references to this object where they get recorded all the way down and up your code base. It doesn't make sense. It doesn't affect the behavior of your code. So it's just easier to use a global and less intrusive for the surrounding code. So right off the bat, most people, when you talk about globals, they go straight to singletons. And actually, globals and singletons are different, or at least in the definitions and usages that I've dug up. So a singleton is a class that can only have up to 1 instance. Okay, it's a property of the class. A global is a variable that has global scope or global access. More technically in C++ parlance, you could say it's a variable that is at namespace scope. I mean, that's sometimes a variable can have global access without being at namespace scope. That's okay. So these two are actually orthogonal. You could have any one or both without the other. A singleton that's not a global is rare, but that could exist as well. But lots of globals are not singletons. And in general, I'll come back to this point, but singletons are even worse than globals, and I discourage them. And I'll explain a bit why later. Okay, so compiler versus linker. So C++ developers, in my experience, really, really like the compiler. They like to talk about the compiler. They like to argue about the compiler. The compiler is getting updated all the time. We had C++ 11, then 14, then 17. It's really interesting. But the linker, I mean, it does get worked on, it does get updated, but it's sort of this thing that has been around for a very long time. C++ was always designed to work with C linkers. That was a big part of the original design. C++ code written today in C++ 17, you could probably use linkers maybe before I was born is an exaggeration, but probably not by much. So this leads to weirdness. And if you don't believe me that C++ developers really like the compiler more than the linker, anytime you Google for help, you'll see that any question that involves the C++ standard and compiling and the compiler, you will find 10 people on Stack Overflow with 100,000 rep arguing about the correct interpretation of the standard. When you Google for help with the linker, usually you can't find any answer, and when you do find an answer, it's got like 2 upvotes or something like that. So it's a lot harder to find out how you should be doing things. Okay, so here's my example. So here's code that looks pretty innocent, or at least it may look innocent to some of you if you haven't encountered this problem before. So let's start with a static library. So I show the header and the CPP contents in the same code block, just for simplicity. So in the header file, we're just including a string. We've got our pragma once. We declare a global with extern. And then in the CPP file, we define the global after declaring it in the header file. So far, so good. Okay, so now we have a shared library. And if you're a little fuzzy on static versus shared libraries, I'll also talk a little bit about the difference there shortly. So what does the shared library do? Well, it has a function that basically just gets this global that it gets from the static library. So the shared library depends on the static library. And then finally, we have an executable. The executable depends on both the shared and static libraries. And it's just going to try to print the string. It's going to try to print the string that it gets directly from the static, and it's going to try to print the string that it gets directly from the dynamic library, the shared library. Okay, so I'm curious, how many people would be able to build this from memory? I'm just curious. Hands? A few people? Not too many? I mean, I had to look up all these commands. I mean, we're used to just writing some C++ code, and then we just fire off our build command. We have a build engineer at our company. He tells us what to do, or we use CMake. And I was very careful here. Many commands that you might issue the compiler, and by the compiler I mean basically G++ or Clang++, they actually invoke the compiler and then the linker, depending on what you're doing. So here, I've separated everything. So we had three things that we were interested in: the static, the shared, and the executable. So I have 6 commands. 1 to compile the object code, and 1 to produce the actual target. So first I compile the CPP file. Then I produce a static library with this command called AR. Next, I compile the code for the shared library. I link it against the static library, so that's what that looks like. And then finally, I compile the code for the main executable, the object code. And I link the executable against the static and shared libraries. So when I do this and I run it, any guesses as to what prints out? Or what happens? Well, actually, this program will segfault. So again, if you've encountered this problem before, maybe you kind of had a feel where this was going, but this code seems very, very innocent. And yet, this segfaults. And it actually only segfaults if you build it this way. If you only use static libraries, if you only use shared libraries, you're going to be okay, which in some ways makes it worse because you find the problem later. And this is probably a good place to point out that as far as this stuff is concerned, a class static variable is still a global. So that seems like a very reasonable thing from a software engineering point of view, right? If you are writing a class, let's say the class parses JSON. In JSON, true is a literal that has to be parsed out as a Boolean value. Maybe you would have a class static constant string, which is set to true. And that seems totally reasonable and harmless, but that can cause these segfaults. And it does. Okay, so let's try to understand what's actually happening. So I suspect that a lot of C++ programmers have written a class like this at some point in their lives. Personally, I call it informer because it informs on everything that it does. So here, when it's constructed, it will print, and it will print its address. When it destructs, it will also print and print its address. And it also has a get method, which just returns its address too. Why not? So I make that change, and I also will change my main. I mean, there's no string to print out anymore, so I'll just print out the address. And let's try to see what's going on with these global objects. Okay, so we're not doing anything interesting anymore, like allocating memory, so we don't segfault. But here's what the program prints out. So one expectation might have been that you'd have 2 copies of the global, which was actually a very reasonable expectation, but it's wrong. There aren't 2 copies of the global, but the constructor runs twice in the same spot, and then the destructor runs twice in the same spot. So it's not very, very hard to see that this is going to cause big problems. If you have a string, what's going to happen is you're going to allocate some memory, set some pointers, then you're going to allocate again and set the same pointers to the new allocation. So that memory is gone forever now, you leaked it. And then you're going to call delete on the pointers in the string, and then you're going to do that a second time with the same pointer. So that causes a segfault. That's not a good thing to do. Okay, so this is where we take a quick detour. and try to talk a little bit about the linker. Okay, so how does a linker work? And this is very, very simplified, I'm assuming. I don't know. I assume it's simplified. This is kind of like a spherical cow model of the linker. You provide a link line. The link line has a bunch of targets. The linker marches from left to right. And you can think of the linker as like it keeps a little notepad or a table. And every time that it encounters a target, that target has a symbol table. And the symbol table basically says to the linker, look, here's a list of all the symbols that I need, whose definitions I don't have, but I refer to in code. And here's a list of things that I do have that I provide in case anybody else needs it. And it marches left to right, and every time a symbol is needed, it adds it to its little list. And every time that a needed symbol is provided by a new target, it then does one of two things. And this is the difference between static and dynamic libraries. If the library is static, then it basically copies and pastes the object code into whatever target you're trying to make. So when you link against a static library, you copy and paste the code, it becomes part of your executable. That's why you don't need to ship a static library with your executables. If it's a dynamic library, then it basically just checks the box and it politely says, thank you, this symbol is going to come from this shared library, and then it tells another entity, it depends on another entity called the loader. And the loader will fetch this at runtime by loading the shared library the moment the executable runs. So that's our static and dynamic libraries. Okay, so I mentioned symbol tables. Maybe we should take a quick look at a symbol table. So the easiest way to look at a symbol table is to use a little command line application called nm. And usually you'll want to pass the --demangle flag so you can read the output more easily. This is symbol table. I'm actually not sure for which version of main, but the idea here is you can see there's a list of symbols and they're marked with various letters on the left. Some of these letters are more important or less. I'm just going to focus on 3 of them on this slide. So the U is undefined symbol. So this is basically saying I need this. So for instance, the main executable doesn't define this global g-informer. It needs to get it from somewhere else. W is a weak symbol. So this is a symbol that's defined, but it's basically one that's defined with like a function that would be defined with inline. And inline, as we know, lets you have multiple definitions of the same thing. So the W is related to that. And T is just a regular defined symbol. Again, for our purposes here, the difference between W and T is not too important. But basically, needed symbols and provided symbols. That's the key thing in the symbol table. Okay, so if we just take this very, very simple mental model and we apply it to our example, what do we know? Well, when we build the shared library, we build it against the static library. And that means that the code from the static library gets copied and pasted into the shared, or at least the code with regards to the global. When we build the executable, if I were to go back and you looked at the link line, you might notice that I linked in the static first, and then the dynamic. And remember I said the linker just marches from left to right. So the moment that it encounters a symbol that's provided in multiple places, it's just going to take the first one that it meets. And if it encounters it again, it doesn't care. So the main executable is going to get that symbol from the static, the way that I built it before. So it's also going to get a copy. And we're actually going to come back to what a copy means exactly in this case. So you could ask, well, now that we know that the link order actually matters, what if we change the order of arguments? So here, what if I link dynamic and then static? Now when I run it, everything just works. So, I mean, this is, again, another way in which the problem can basically be hidden. If you get all of your linker order arguments right, you may be able to prevent these issues, but you're probably not staring at your linker command line order. So that's probably not a good way to solve the problem. Okay, so let's try to dig a little deeper and figure out what's actually going on. Where does a global actually get initialized? So here I use objdump, and I just dump the assembly. And there's a lot of stuff. But if you search through carefully, you will find basically something like what I have here. So there's this section which is kind of suggestively named global var init. And this is a section which is used for things that have to happen immediately when the shared library is loaded. And one of the things that you can clearly see there is a call queue, a call to the constructor of Informer. Now, the shared library in both of our examples, the one that worked and the one that didn't, it was built the same way, right? So the shared library will always try to initialize the global. Okay. Now how about the executable? Well, the executable will sometimes try to initialize it. And what I mean by that is if you link against the static first and then you run objdump, you will find code like this in the executable. Again, it's very similar. It calls the constructor. One thing that you might also notice here is that it actually loads the destructor into this kind of variable cxa at exit. That makes sure the destructor gets called when the program ends. If you change the link order so that the shared library is first, the executable will not have this code, and then it doesn't run it. So we actually don't get two copies of the global. What we get are, you only have one copy of the global, but the problem is there's more than one entity in your program that thinks it's their job to construct it and destruct it. So, you know, in a way this is worse. Instead of having two correct globals, which is not great if you actually want it to be a global, but now you have a global whose constructor ran twice in the exact same spot in memory and then destructed. That's pretty bad. Okay, so, you know, there are a lot of things you could say here, right? Like you could say, well, only write, you know, globals in shared libraries, or only use either static or shared linking, don't mix. You know, you could say all those things, but what I would rather say is, what if we just wrote the code so that this could never happen? Because a lot of times the people who might write the code are pretty far removed from the people responsible for building it. And at a large company, you know, maybe you originally only used it as a shared library, you never found this problem. Someone downstream of you uses it as a static library. So, you know, robust code is better. So actually, a friend just sent me this link a day or two ago. So in Boost log, there's this caveat. If your application consists of more than one module that use Boost log, the library must be built as a shared object. So I haven't actually dug into the code. I don't know if this is exactly the reason, but it sure smells like it. Especially since, you know, logging is a very common use case for globals. I mean, I would prefer to see this written, right? You can build against Boost log however you want, and everything's going to be fine. So, okay, so what do we do about this? So in C++ 17, it's actually really simple. We have the keyword inline. Inline, you're probably more used to thinking of inline as, well, we can just put this in the header. That's true, but it also means that regardless of whether you put it in the header or the CPP, and I'll come back to that point, you only get one copy of the global. And this just works. And I'm going to come back to why this just works. Okay, what if you're not on 17? I mean, I'm not on 17. I'm sure many people here are not. So here's a lazy solution, literally lazy. You basically have a static local, and your function returns a reference to it. And that's it. So this kind of popularized in the Meyer singleton. So there's some good things about it. There's some bad things about it. It's lazy, so it always gets constructed when you need it. But if you're replacing an existing global, you now have to add these parens everywhere. That could be annoying. Bigger concern, there are some performance questions with this. So first of all, you're going to have a branch every single time you access this global forever. There's also going to be some extra code there to actually atomically ensure that this is initialized only once in a thread-safe manner. And also, some people this may be an issue, for some it may not, but whenever you do something lazily in a complex program, you are taking the chance that it's going to happen at a really inconvenient time. So if you care a lot about performance, lazy may not be great. So I've actually had plenty of issues with lazy things happening at the worst possible time, and it's not good. Okay, so what's one way to solve this? Well, we could just stop being lazy. So this is a neat trick that's very simple, but I haven't really seen, suggested very many places or anywhere. So you basically still have your function, but now we just declare a very simple static global reference. So this is basically just a pointer. And we initialize it with the function. And this just makes everything work out. The function is forced to be initialized, so now this is not lazy anymore, which might be good or bad. And also, you're going to access through the reference, not through the function. So there's no Boolean check anymore. The reference is basically a pointer. You have a pointer straight to your global. You just access it, no Boolean. OK. Now, if you really, really, really care about performance when accessing a global, which might be a code smell in the first place, this mess is a little faster, produces slightly better assembly. And so what on earth am I doing here? Well, before I said, hey, inline just works, I'll explain why later. So if you take a step back and think about it, even before 17, linkers must have known how to do this correctly. And the reason why is because templates, generally speaking, have to be defined in header files. And a class template could have a static variable. And that static variable has to be handled correctly. So there's actually already a facility in linkers built in that lets you correctly link as long as you use a static of a class template. But there's no easy way to access it. And it's a little funny in a way because templates are implicitly inline. So there's actually this implicit inline keyword here that we weren't able to make explicit until 17. As you can see, this is a lot of boilerplate. It's kind of annoying, but like I said, it is a little faster than the previous slide. I'm sorry? Missing the static keyword. Oh, man, that's a pretty bad bug. Yeah, thank you. So that should be a static std string, g_stir. OK. So all of these techniques will basically help your globals not be double constructed or double destructed. If you're on 17, just use inline. If you're not on 17, pick one of the three. OK, so the last thing that I'm going to talk about, kind of briefly, I guess, is interdependent globals. So if you just use one of those three tricks, it's actually very easy to write code that will always get constructed and destructed properly, no matter how you build, for one global. The bigger nasty problem is what's called static initialization order fiasco. So in C++, there's no guarantee on in what order different translation units are loaded. So because of that, once you have globals that depend on other globals, particularly in their constructors and their destructors, you really have a mess. So unfortunately, there is no silver bullet to this that I know of. But what I'm going to do is basically point out a few pitfalls and alternatives. And if you keep the number of globals in your application small to start with, then applying these judiciously should probably help you avoid most SIOF problems. OK, so the best thing to do is to just not have interdependent globals as much as possible. And earlier in the talk, I mentioned singletons versus globals. And I said singletons even worse than globals. So what I mean by that is that when you write a singleton, you're taking all this useful functionality, and you're locking it inside of a thing that can only have one instance. And that's very hard to justify. I mean, if you have a logger, why are you writing the logger as a singleton? Like, there's no fundamental reason why you can't have 2 or 3 or 4 or 5 loggers in a program. Maybe you want to have one global logger for convenience. So here's an example. Like, let's say I'm writing an intrusive profile data. This is intended to be used as a global, so that I can write my intrusive profiling macros. So in the first line, one option would just be to use the global logger and log something in the constructor. But now I have a dependency between two things that are going to be global. Another option is you could just take the logger class and say, well, because this intrusive performance data is itself a global, it's special. I'm just going to give it its own logger instance, and that may or may not be OK depending on your use case, but it just completely removes that dependency. So now you'd have like one logging file for your main program, you'd have a different one for your intrusive profiler. And in many situations, that's OK. And that really actually makes things simpler. Another thing, so when people talk about inline coming in 17, a lot of people say, well, it's great for header-only libraries to define globals. That's true, but actually, I'm going to say, I think you should always define your globals in header files. That may seem a bit weird, but because of SciOff, right, consider that if you define a global in a CPP file, and you don't provide any kind of like special hook or function to force initialization of that global, there is no way that anyone else can ever use that global in their globals constructor. It's not possible because there's no way they can force that global to initialize first. If you define it in a header file, then you just pound include it. And because it's going to show up before your global, it will always get initialized before yours. Okay, a couple of quick code examples. So laziness and destructors. You have to be really careful. Lazy globals are great for some things. They're not so great when you want to do something in a destructor. So here's an example where we have a lazy logger. Okay? So it says constructed, logging, destructed. So in this sample program, I have another global called foo, okay? Foo f, and then my main program tries to do some logging. So what actually happens here, right? Foo gets constructed first, because it's first, then main runs. Main tries to use the logger, it does some logging. Now, at this point, we fall off the end of main and all the globals get destructed. So logger was constructed second, so it will be destroyed first. So the logger gets destroyed, and then after that, foo gets destroyed. And that means that foo is now trying to log to a logger that doesn't exist anymore, and that's no good. So there's that caveat with laziness. And finally, so here, if you have a header that defines globals, you should include it in your own header. And to see what I mean by that, let's look at this example. I've condensed this all into one file, but it could be a multi-file example where the translation units happen to be set up in this order. What happens here basically is that I've decided to pound include IOStream in my CPP file. But in my header file, I defined a global. And what happens is that actually the program will see my global before the IOStream globals. And if my constructor happens to use that global, there's yet another way to get a segfault. So the advantage of header files is they enforce ordering. And when you're dealing with globals, that's very, very important. Okay, so the end of the talk, conclusion. Just knowing the very basics of how a linker works, having like a rough mental model, being comfortable with NM and objdump to debug these sort of things, very recommended. Anytime you're creating a non-trivial global, so something that's not an integer or a Boolean, use one of the techniques that I discussed. Either if you're on 17, just use inline. Otherwise, use something else. Be aware of SciOff. Try to leverage header files to avoid dependency ordering problems. And just think very carefully before you introduce dependencies between globals, because you're going to have to think about that dependency forever if you introduce it. So maybe just better to not. So thanks very much, and any questions?
One small additional point, as a useful thing, you can also just not have your globals destructed. If you do the lazy pattern with new to put them on the heap, your destructors aren't run. And it's not really a memory leak because the pointer's still there and the entire process is coming down, so the OS will reap it. It is substantially safer than having your destructors run.
So a couple of thoughts on that. I'm not a huge fan of that personally. It makes it harder to find real memory issues. But even aside from that, memory is not the only resource. And actually, very common when you're writing a fast logger is you're not going to log things immediately. You're going to have a buffer. That buffer needs to be flushed, and that will happen in the destructor. So, but I agree. I mean, depending on your use case, that may be the way to go. Yeah. Oh, next question.
Yeah, just one addition. The way you describe the linker does the ordering resolution is specific to Unix linkers.
Yes.
The market
Sorry.
linker doesn't work that way, and actually LLD doesn't work that way either. So that's
Is LLD the Clang linker?
Yeah.
I forget the name. Yeah, so the Clang linker introduced a small wrinkle where it still goes left to right as far as I know, but it picks up defined symbols before they're actually needed. So you don't need to worry that every single symbol table that defines something is after where that symbol is needed. But as far as I know, that's the only difference.
Yeah, exactly. So with traditional Unix linkers, you can get in the situation where you have to specify a library multiple times.
Yes. Yeah.
And on Windows and with LLD, you don't have that.
Right. I actually meant to prefix the talk. I'm kind of sorry. So these issues are, as you people probably realized, Linux or Mac OS specific. I think that the Windows situation for this stuff is actually a lot better, that it's harder to create these globals foolishly on Windows, but I don't really know. I'm not on Windows much, so. No.
Hello, just wanted to mention one maybe slightly neat idea, but now with the const expert, that overhead where we have to ensure that the constructor is only called once, that overhead doesn't need to be paid because it's essentially the old C-style type initialization.
Yeah, but I don't think you can mark the constructor for something like a string const expert, right? Because it can do a heap allocation.
Yeah, for the constructor, it wouldn't be possible, but well, it might not be possible in all cases, but in the case that it can, it's now a way to also be able to not pay for that overhead.
Yes, yeah, that's true.
I have still a feeling that this is the problem of a build system, because I find it an elegant way to demonstrate the problems with global variables, but you have duplicated symbols because you link static library to dynamic, and then you link again the static library to the executable. So if you have the functions there and you use both in executable and dynamic library, you get build error, to what I understand. So I think the root of the problem is linking twice to the static library.
Yeah, I mean, it's one of the roots in the sense that if you didn't do that, you wouldn't observe the problem. The problem is that basically if you don't do that, and this is actually the build engineer at my company said something very similar to this. The problem is that then what you're basically saying, and he says this happens a lot in practice, that whoever's distributing the shared library will say, okay, I need this library with the global in it, but now it's your responsibility as the end user to provide it because it has globals and we're not going to link it in because you might get duplicates, so now it's your problem. So you can do things this way, and if you fully control everything from end to end, it's one way to go about it, but I mean, I don't think it's optimal. I think each target could be built by someone else, and each target should include its own dependencies. And if you think that those two are both good requirements, then this kind of thing can happen. But again, it's a matter of approach. I just prefer to write code that will always work. That's,
Thank you.
no problem. Yep.
In the very first example, when I saw that we have this object initialized twice from the main executable and from the shared library, this address of this object, what address is it? Is it in the segment of the main executable? Is it in the segment of dynamic library, or is it something completely different?
So in this example, the segment will, in the example that breaks, the global will live in the main executable. And I didn't really have time to get into this, but basically when the loader loads a shared library, it will just quietly discard any symbols that it's already seen before. And the global itself is a symbol. So this is actually why you don't get two copies of the global. The global will load the shared library, it sees the global symbol, it's already got the global symbol, it ignores it. But then it still runs the initialization code. And since that global symbol is already defined, it runs it on the same one. So in short, it would have been in the static in the example, in the main executable in the example that I gave. The one from the shared library would physically exist inside the space of the shared library, but it would never have been used by the program. That is another caveat that I didn't mention up front, maybe I should. I mean, I didn't get into DL Open with this talk. I've used it before, but I'm not very familiar. So I actually don't know the answer to your question. No. Okay. Well, thanks very much.